Okay, so this lecture is your final lecture before. This isn't your final lecture. This is the final lecture in your midterm syllabus, lecture 5. So today, what we're going to do is we're going to look at triangular matrices, right? And we're going to use ideas about triangular matrices to decompose any invertible matrix into a lower triangular matrix and an upper triangular matrix. Okay, so first what we need to do is we need to define what a triangular matrix is. Right? So a lower triangular matrix so this chapter is titled A equals LU factorization. Okay, so a lower triangular matrix is a matrix, let's call it L, where all the entries below the main all the entries above the main diagonal are 0. So you have L11, L12, L22, L3. Sorry, this is L21, L31, L32, L33, and so on and so forth until Ln. So L is an n by n matrix. This is Ln2, Ln3, Lnn. Okay, so the rest of the entries are 0. So the entries above the main diagonal are all 0. Okay, so a lower triangular matrix, in other words, a lower triangular matrix is a matrix for which Lij equals 0 if I is less than j, right? So the column number is greater than the row number, right? So for example, L23 is greater than 0, is equal to 0. So 2 is less than 3. So this is how you define a lower triangular matrix. This is how you define a lower triangular matrix. The upper triangular matrix is defined in just the opposite fashion. An upper triangular matrix, U, let's call it U, is a matrix for which everything above the main diagonal is everything below the main diagonal is 0. And everything above the main diagonal may or may not be 0. U1n, so on and so forth, right? So this is an upper diagonal matrix. So the precise way of defining it is Uij equals 0 if I is greater than j. This is how you define an upper triangular matrix. Okay, so you have lower triangular matrices and upper triangular matrices. The third thing we need to define is a diagonal matrix. A diagonal matrix is, okay, so let's go D11, D22 DNN, right? So a diagonal matrix this is a diagonal matrix. All entries that are not on the main diagonal are 0. And of course, the most famous diagonal matrix that you know of is the identity matrix. The identity matrix, right? 1, 1, and everything that is off the main diagonal is 0. All right, so all of these elements are 0. So this is the n by n identity matrix. Okay, so for this lecture, we will be needing certain properties of triangular matrices. We will need the fact, and you will be proving these properties in your assignments. So you will, first of all, you will need the fact that the product of two upper triangular matrices is upper triangular. This is true, and then when you replace upper by lower, the product of two lower triangular matrices is also lower triangular. Okay, so what I'll do is I'll write this in the bracket, right? So the product of two upper bracket lower. Okay, so the product of two upper triangular matrices is upper triangular, and the product of two lower triangular matrices is lower triangular. The second fact that you will need is the inverse of an upper and bracket lower triangular matrix is in bracket lower triangular. So this is another question on your third assignment. So this is on your third assignment. One way to try to prove this is by trying to invert the matrix using this augmented matrix. And you will notice that when you, of course where this exists, where it exists, meaning where the inverse exists. If the inverse of the upper triangular matrix exists, then of course it's upper triangular. If the inverse of the lower triangular matrix exists, then it's lower triangular. So if U is invertible, if this is invertible, then of course this becomes, then when you, by the equivalent statements about matrices that we looked at, by performing elementary operations, when you perform Gauss-Jordan elimination, this becomes the identity matrix, right? And I becomes U inverse. And you will notice that U inverse is upper triangular. That's one way to prove it. Okay, so now we move on to our main topic, which is A equals LU decomposition. So we've covered upper and lower triangular matrices. So now what we're going to do is we're going to try to factorize invertible matrices into upper and lower triangular matrices. Okay, so we start off with a 2x2 matrix A. Okay, let's call it 2 1 8 7. And because the reduced row echelon form does not give you a 0 0 on the second row, we know that this is invertible because the RREF is going to give you 1 0 0 1. Okay, so but when you perform Gaussian elimination, right? Perform Gaussian elimination. By row exchanges. Okay, Gaussian elimination without row exchanges. Okay, so when you do this without row exchanges, you end up with 2 1. Of course, 8 minus 4 times 2 is 0. 7 minus 4 times 1 is 3. 0 3. Now this matrix is an upper triangular matrix. Okay, so we will call well, that's because notice that everything below the main diagonal, which is 2 3, is equal to 0. So and of course we need so we've got the upper triangular matrix. So how are we going to get the lower triangular matrix? So we get the lower triangular matrix from the elementary matrix, and I'll show you how we get this. Okay, so just a moment. Okay, so with just one row operation, right? What was the row operation? R2 goes to R2 minus 4R1, right? With that row operation, we brought A to U. Now, what is the elementary matrix that corresponds to that row operation? Okay, so what we'll do, we'll call the elementary matrix 2 1, E21. Why? Because it makes the entry in the 2 1 in 2 1 equal to 0. The 2 1 entry, the entry in the second row and the first column, it makes that 0. So we'll call this E21. So this is equal to 1 0, and then you have minus 4 and minus 4, and you have 1. Okay, so I know that E21 times A should give me U, right? There's this upper triangular matrix. You can check, right? So 21 times 1 minus 4 should give you minus, I think, okay, sorry, 1 0 times 2 8 should give you 2. 1 0 times 1 7 should give you 1. And then minus 4 1 times 2 8 should give you 0. And minus 4 1 times 1 7 should give you 3. Okay, so this is correct. Now, and notice one thing, that E21 is lower triangular, right? Because there is nothing, there are no non-zero entries above the main diagonal, right? So in that case, A equals E21 inverse times U. Now, since E21 is lower triangular, E21 inverse will also be lower triangular because of the theorem that we stated here and you will prove in your assignment. So if this is E21 inverse is 1 0 plus 4 1, because E21 corresponds to this, to a particular elementary row operation, R2 minus 4R1. So E21 inverse must correspond to the inverse of that row operation, right? So R2 plus 4R1. Okay, so, and then of course you have U. Oh God. Okay, so U, which is of course given by 2103. 2103. So notice that I have decomposed A into L and U. Okay, so now what we can do is we can try this with a more complicated example. Let's try a 3x3 matrix, right? So let's start with so let's find ourselves a 3x3 matrix. Let's call just give me a moment. Okay, so this method, of course, works because this method works only because the inverse of a lower triangular matrix is a lower triangular matrix, and also because the it also works because the product of two lower triangular matrices is a lower triangular matrix. Okay, so so let's look at this example. A equals 2 1 0 1 2 1 0 1 2. Now, how many, to bring this to row echelon form, how many operations do we need to perform? Well, we need to make this 0, right? We need to make this 0. we need to make this 0, and this is already 0. So we need to perform two elementary row operations, right? So in order to make this 0, right, what do I need to do? I need R2 goes to R2 minus 2 2R2 minus R1, right? So what this should be is R2 goes to R2 minus half R1. So what you're doing is you're subtracting half of the first row from the second row, and to bring this to 0, you have to do R3 goes to R3 minus half R2. Actually, let's do this first. Right, let's do R2 goes to R2 minus half R1. So if you do this, then A goes to R2 minus half R1. This becomes 2, 1, 0. So 1 minus half of 2 is 0. 2 minus half of 1 is 3/2. And 1 minus half of 0 is 0. And this, of course, is 0, 1, 2. The elementary matrix corresponding to this, right, corresponding to this transformation is, we'll call this E3, we call this E3, E21. Why? Because it makes this 0. It makes it 2, 1 element 0. Right? So the elementary matrix is then equal to what is okay, so 1, 0, 0, right? So, and then of course you'd have minus half, 1, 0, 0, 0, 1. And the elementary matrix that corresponds to, okay, so the next thing we need to do is we need to make this guy 0. Alright? So the way to do that is R3 minus 3/2 R2. That makes it 2, 1, 0, 0, 3/2, 0, 0. So it's not 2/3. It's not 3/2. It's 2/3. Right? So 0, 0, and then this stays 2. Right? So of course this makes E32 equal to 0. The 32 element equal to 0. So we're going to call this 1, 0, 0. E3. We're going to call this E32. So this becomes R3 minus 2/3 R2. So 0 minus 2/3, 1. Right. So the product of these guys, right? So E32 times E21 times A equals sum, not sum, equals an upper triangular matrix, which is given by 2, 1, 0, 2, 1, 0, 0, 3/2, 0, 0, 0, 2. Right? So that's the I'm sorry, let me write this more clearly. Let's erase this. Two, 1, 0. 0, 3 over 2, 0. 3 over 2, 0. 0, 0, 2. Okay, so this is my U. Notice that everything below the main diagonal is 0. So this is an upper triangular matrix. Alright, so now that we know that this is now that we have the upper triangular matrix, let's look at the lower triangular. Let's find the lower triangular matrix. So A, remember, you should remember this, right? So this guy, this is equal to y inverse x inverse. So A should actually be equal to E32, E21, the product of these guys inverse times U, which is actually the same as E21 inverse E32 inverse times U. Now, E21 inverse. What is E21 inverse? What is E21? E21 is this matrix, right? So 1, 0, 0. Okay. So E21 inverse is a matrix that corresponds to the inverse transformation, to the inverse elementary row transformation. 1, 0, 0, half 1, 0, 0, 0, 1. This is E21 inverse. And what is E32 inverse? E32 inverse is the inverse of this guy, right? So this should be equal to 1, 0, 0, 0, 1, 0. 1, 0, 0, 0, 1, 0, 0, 2 over 3, 1. Alright? Times, of course, U. So notice that both of these guys, both of these matrices are lower triangular matrices, both E21 inverse and E32 inverse. Of course, this is what you would expect. So once you multiply these two guys, you get 1, 0, 0. Here you get half. Here you get 1. Here you get 0. And here you get 0. You get 2 over 3. And here you get 1. And U is, of course, as before, given by this guy, 2, 1, 0, 0, 3 over 2, 0, 0, 0, 2. So 2, 1, 0, 0, 3 over 2, 0, 0, 0, 2. So this is my L and this is my U. And notice how I've managed to notice now that I've managed to break up U into into the product of a lower triangular matrix and an upper triangular matrix. So what is the algorithm? The algorithm is simply this. You first bring down, you first take A into row echelon form, right? So you have a matrix A, take it to row echelon form, form. Remember I said without interchanging rows. Right? So you're not allowed to do RI and RJ, right? This is not allowed. Not allowed. Right? And then at each step, then what you do is at each step, right, you write down the elementary matrix, right? So of course with each because you'll be doing elementary row operations, and for each step you will need an elementary matrix. And then the next thing you do is you write the reduced row. So the reduced so the row echelon form is obviously upper triangular. The row echelon form is upper triangular. And of course this may be written as, let's say you have K row operations, right? So this can be written this way, and then the elementary matrices are all lower triangular. They're all lower triangular. Why? Because we excluded what we did is we excluded interchange of rows. We only allow subtracting one row from some multiple of the other. So then you can write A as this inverse times U, but then this is equal to E1 inverse all the way to EK inverse times U. Now these inverses, right, E1 inverse, E2 inverse, all the way to EK inverse, these are all lower triangular matrices. Now since because the original matrices E1 to EK, they're all lower triangular themselves, so the product must also be lower triangular. So this can be written as LU, lower triangular times an upper triangular matrix. So this is how you decompose a matrix into an upper and a lower triangular matrix. Right now, why is this? What motivates us to do this, and why is this important? It's important because of the following reason. Now, when you're doing applied linear algebra, all right, when you're applying linear algebra to economics or the sciences, you will encounter systems of equations with hundreds or thousands of variables, right? So you might encounter an equation that looks like this. Okay, AX equals some vector V, where A is A could be A is a 1000 by 1000 matrix, right? Now, so since if A is a 1000 by 1000 matrix, now these equations, right? Well, a thousand by 1000 matrices and 1000 variables, they're very common in linear algebra. In applied linear algebra. So what we do is okay. So now, if you were to apply ordinary Gaussian elimination, right, or ordinary Gaussian elimination, ordinary Gaussian elimination, how would you do it? How many operations would that take? You? So let's say you start off with a n by n matrix A, right? Right. So you have your entries here. These are the entries of A. So this is your A. Now, the first operation. What is the first operation? What's the first thing you do? You start by making all these numbers under this pivot point equal to 0. Right? So how many operations does this take? All right. Now, and by an operation, of course, I mean a multiplication and a multiplication is an operation, subtraction is an operation. So if you want to make all of these 0, right? What you need to do is you need to first multiply this row, the first row, by some number, right? Multiply this first row by some number, so that this minus the first row, the second row minus the first row, gives you 0, yields 0 here, right? So multiplying the first row by a certain number means multiplying all the elements in the first row by that number. So you have n operations, right? And then what you need to do is you need to subtract all the other rows, right? So for example, you need to subtract the second row and the third row from the first row and the fourth row from the first row. So that gives it, for each row, that's a for each row that you have, right? That's so for each row there are n numbers being subtracted, right? And there are n minus 1 subtraction rows that you need to subtract, right? So each subtraction is n minus 1, right? So n square minus n subtractions, right? So since you have n square minus n subtractions, now consider this. If you have a if you have a matrix that's very large, right, of the order of a 1000 squared matrix, right? How would you how would you okay, let's rephrase the question. If the matrix is very large, then n square is likely to be much greater than n. So for example, if you have a matrix that's 1000 by 1000, right? So 1,000 square is much greater than 1,000. So if that is the case, n square minus n can be approximated by just n square, because this is 1,000 square minus 1,000. So 1,000 square is much greater than 1,000. So this is approximately equal to n square. So the first row, so in order to in order to make pivot points out of the first row, you need to do n square operations. And in order to make everything zero below the pivot point in the first column, right? This column, you need to make n square operations, right? And let's say this is the pivot point in the second row, second column. Let's call this A21. So everything below this is 0. So there are of course n minus 2 zeros here, and so on and so forth. So in total, right? In total, you will have to make approximately n square plus n minus 1 square, or approximately, or which is equal to 1/3. The formula for this is actually 1/3 times just give me a moment. This is equal to 1/3 times n times n plus half times n plus 1. But the leading term is 1/3 n cubed. Remember, I said that since n is large, n cubed is much larger than n square, which is much larger than n, and so on and so forth. So you have to do this many steps, right? 1/3 n cubed, right? So in algorithmic language, we would say that this algorithm is O(n) cube complex, right? So since that is the case, now if let's say you have a 10 by 10 matrix, right? Then you would do approximately 1,000 steps, right? For a 100 by 100 matrix, then that would become 1, 5, 6. So that will become 1,000,000 steps, right? For a 100 by 100 matrix. 100 by 100 matrix. Notice how the number of steps just blows up, right? As you increase the number, as you increase the size of the matrix. So now, and of course, these are order of magnitude calculations. These aren't exact calculations. So what we need to do is we need to reduce the number of steps, right? And especially if our matrix is sparse, meaning if our matrix has many leading zeros on the columns below. So for example, if you have a matrix that looks like this, right? A big matrix, 1, 0, 0, 0, 0, 1, 2. So if it has many zeros in it, right? A sparse matrix is one that has many zeros, 0, 6, so and so on and so forth, right? So this matrix is called a sparse matrix. sparse matrix. And what this does is so if you have a sparse matrix, you can apply LU factorization and get away with solving a particular set of equations with far fewer steps. How does that work? What you can do is once you have factorized something in terms of LU. So, for example, if you have AX equals C, right? AX equals V, right? System of linear equations. So you can call this as LUX equals V, right? So what we're going to do is we're going to call UX equals C. We're going to call UX C. So then that makes this LC equals V. So first we solve. So first solve LC equals V. Then solve UX equals C. So that's how you get your X. That's how you get your X. Get X from here. So okay, so for example, if we have okay, so for so we have just give me a moment. Probably need a few more pages for this. Okay, so let's say we have a system of equations that looks like this. U plus 2v equals 5, and we have 4u plus 9v equals 21. So what is your A? A is of course the coefficient matrix 1, 2, 4, 9. This is my A. What is my V? V is equal to 5 and 21. Alright, so first thing I need to do is I need to express A as a lower and an upper triangular matrix. So you can, well, you have A L equals 1, 0, 4, 1. This you have to work it out by yourself. And U equals 1, 2, 0, 1. So LU, does this give you A back, right? 1, and then 2, and then you get 4, and then get 1. 9. So yes, this does give you A back, right? So now the question is, what is your C, right? So we have to start with we have to start with UX. We have to start by solving LC equals B, right? The lower triangle, we have to solve the lower triangular system, and then we solve the upper triangular system, right? So remember we said UX equals C, right? So if UX equals C, then LC must equal V. So let's see, C equal C1, C2. So L is this. So LC equals V can actually be written as C1 equals since B is 5 and 21, C1 equals 5 and 4 C1 plus C2 equals 21. So that this last equation gives us C2 equals since this is 20, so this gives us C2 equals 1. Right? So C gives us 5 and 1. So C is this vector, 5 and 1. Now we need to, what we need to do is we need to solve UX equals C. UX equals C. Okay, so remember what U was? What was U? U is 1201, right? So U is 1201 times XY. This gives me C, which is 51, or X plus 2. Well, let's call this X1 and let's call this X2. So X1 plus 2X2 equals 5 and X2 equals 1. So which gives me X1 equals 5 minus 2, which is 3. So in 2 steps I get X equals 5 and 1. Okay, so this works better when, of course, you have when you're working with. I mean, you can see the advantage of the method more easily when you're working with very large matrices. Okay, so let's do another example. So let's say we have a matrix P, right? This is a special type of matrix. It's known as a Pascal matrix, and the entries are derived from Pascal's triangle. So if you have a matrix P, let's call it actually. So this matrix has P equals 1 1 1 1 1 2 3 4 1 3 6 10 and 1 4 10 20. Okay, so this I can write as an LU matrix. So this can actually be written as, I want you to show this, 1 0 0 0 1 1 0 0, right, and then 1 2 1 0 1 3 3 1. Okay, so this is how it can be written. This is how P can be written. Now I want to solve Px equals B. Right? I want to solve Px equals V. So of course the first thing I do is I write this as Lux equals V. So this, I've shown you, this is my U, right? I mean sorry, this is not my U, this is my L. L times, this is my L, times some U, because U is of course the lower triangular matrix, and U is what gives you the sorry, U is the upper triangular matrix, and that is your row echelon form, right? So you should be able to show that you should be able to show that U equals 1 1 1 1 0 1 2 3 0 0 1 3 0 0 1 3 and 0 0 0 1. This is U. Now, since this is your U, and we want to solve Px equals B, and now V is basically 1 0 0 0 transpose, right? So the first thing we do is we set P equal, we find the LU decomposition of P. So LUX equals V. So of course we're going to define UX equals C, right? So then that gives me LC equals V. But since I know what L is, I can write the equation as LC equals V. I can write as C1 equals 1, C1 plus C2 equals 0, C1 plus 2C2 plus C3 equals 0, and C1 plus 3C2 plus 3C3 plus C4 equals 0. So here, this gives me C1 equals 1. This gives me C2 equals -1. This gives me C3 equals 1. This gives me C4 equals -1. Notice how I'm going from top to bottom, right? From top to bottom. Now what I need to do is I need to solve UX equals C. Okay, so LC equals V. Okay, this the thing that we're doing here is known as forward elimination, right? Forward elimination. Forward elimination. Meaning the solution of LC equals V. Now, when we do bottom up, that's called backward elimination. So now we need to do solve UX equals C. So we now know what C is. So UX equals C is of course given U. This is x2 plus x3 plus x4 equals 1. x2 plus 2x3 plus 3x4 equals -1. x3 plus 3x4 equals +1, and x4 equals -1, right? So if you start with the bottom equation, then you get x4 equals -1, and then you go up, you substitute x4 here, you get x3 equals +4. Substitute your x2 and x3 here, get x2 equals +6, and substitute x2, x3 and x4 here, get x1 equals plus 4. So this is known as forward elimination, right? You go from bottom to top. Okay, so that's that for this lesson. You need to be able to, as far as the syllabus is concerned, you need to be able to factorize a matrix into LU, right? An invertible matrix that they give you into L times U, and you also need to be able to solve a system of simultaneous equations using LU decomposition. And for examples, you may of course go through Gilbert Strang's book. There are plenty of exercises that'll help you go over this stuff. So yeah, so that's it. Thank you very much.